So I go just a little bit more to the optical link design. So we'll talk about transmission in optical fiber, so we know how to transmit. We talked about source and modulation and receiver, so we know how to put data and how to detect it. But now, how do actually people build these systems to transmit optical? Okay? So I have to connect 2 points, and I do it using an optical system. So what's important in there? So an optical link basically means that I have to engineer sources, modulation, fiber type, fiber length, amplifier, dispersion, regenerators, maybe receiver, so that at the end I achieve basically a small beta probability. So ideally, I want at the end the exact same signal that I had originally. I transmit a bit pattern, and no matter how long I go, no matter what happens, I want to retrieve the exact same patterns with no errors. That's my target. So I have lasers, I modulate, it goes through some fiber, the signal alternates as it goes through fiber. I have to amplify it, some more fiber, I receive it, and then I want it again. So typical target beta array are 10 to the minus 9, 10 to the minus 12 maybe. That's at the end of the whole thing, okay? What's typical wireless? Do you know this? Anyone knows? What would be a typical beta array that you want in a wireless system?
Be higher than that, I think.
About 10 to minus 6?
Minus 6, yeah.
But you know, as well, like, I mean, an optical fiber goes to 10 gigabits per second. So 10 to minus 6, basically, so a gigabit is about 10 at the power of 9.
Yeah.
So if I have 10 to minus 6, it means that I get about 1,000 errors per second. You know, you have to play with these things. 10 to minus 9 at 1 gigabit means I have 1 error per second. You know, okay, so how do I get the beta array that I want? So how do I check that there is no errors? So the beta array will depend on the receiver here, okay? Because I always calculate the real beta array is on the receiver. So when I get the signal back, I can check what's going on. So we depend on the signal to noise ratio seen by the receivers. So this matches pretty much like optical array electrical. Okay. Then we'll see that the signal error is signal to noise ratio will actually depend on something which is called the optical signal to noise ratio, which is something that I can work through while I'm optical. Okay? So this basically, I can only work with this one. Like, this is related to all an optical equivalent. In addition to that, I have 4 error correction techniques at the receiver. Okay? So typically, I can actually, sometimes I can decrease the bit rate even to 10 and power minus 3. Because I can apply some forward error correction. And this is an example. Okay, so this is a signal which is not coded. Okay. So depending on so this is my input bar. Okay. So this is the input that I measure basically physically. And if I, for example, imagine that you can see that's 10 to minus 4. So of course, if I don't have any error correction, then this is what I get, and this is exactly what I see, 10 to minus 4. Okay? So that basically means I get what I see because I have code. But by using simple code, which is called, this one of those companies that are really slow. So if I have 10 to minus 4, I can correct error so much, that basically I end up with something like 10 powers minus 14. Now this is for a particular system. It looks actually quite good in the case. But I mean, the read solver is actually, it's quite a simple code. It's used for CDs. Yeah, so if you are scratching your CDs, that's an error. But because you have this code, you can correct the error more than you notice. Now, of course, what's wrong with using FEC? That FEC, this one is based on 239, it's called 55239. That basically means I need to send 255 blocks of data in order to send really 239. So this is the real data that I send, and the difference between the two is the overhead that I send. So for example, if FEC has an overhead of 7%, I have 10 kilobit signal, the useful data rate I can use is 9.3, because the rest is used because I have to add more bits. It's the overhead. It's like the same as a routing protocol. I send a packet, and I have an IP header. The IP header doesn't bring any information about the payload. So it's basically, I need to transmit more information, and that's done with Optical that I want to use. Then there are even better codes, super efficiency codes, which should work extremely well. But another one is that if I work at 10⁻3, then I can come up with a signal which is 10⁻6.
Out of curiosity, which kind of codes are perfect?
What's that right?
What kind of codes are supposed to be like?
I'm not too sure actually. Well, I mean, I don't know coding that much. I know there are codes called turbo codes.
Yeah,
I'm
yeah.
sure if this refers to the turbo codes.
But they tend to have higher rates. Oh, that doesn't matter.
Yeah.
It's just me.
I mean, yeah, just found this. Just to explain a little bit what you can do to improve.
And is there more overhead still with super forward error correcting?
I don't know. I mean, it depends. Like some of them are really good. I mean, it is quite amazing how can you correct codes so well. Because I mean, you expect improvement. That's a large improvement. And I think it's all about the fact that you know what kind of noise you can expect. Right? So see, a lot of those are built to expect. For example, Gaussian noise. Okay? And if you get a short noise, you probably totally crap. Okay? But since you expect, I mean, the error code basically depends that if I send a normal, imagine I send a normal signal, I send a certain constellation. So ideally, I could say that any of this can be my signal, my right signal. Okay? Again, this or again this. Now, if an error occurs, okay, by Gaussian, and I know it's a Gaussian error, then I know that probably this will basically be a mistake just by going this way, this way, this way, or this way. That's what's most probable. Okay? What an error corrected code does is that basically I make sure this doesn't exist, doesn't exist, doesn't exist, doesn't exist. Okay? So I basically have a subset of all the possibilities of what I can send. So for example, I can send this one here, and then the next one I can send this one here, because I know that this one is not really liking. And if I receive something which is like this, okay, this is not my good sample, but then I correct it by saying, okay, then it must be this, because this is not allowed. Okay. So I still transmit bits. One is a thermal noise. Now the good thing of being optical is that when you have at optical frequencies, then you don't have thermal noise. Thermal noise only affects at lower frequency. But as you go up, that disappears. However, when you go back to the receiver, that's an electrical device, so for electrical frequencies. So you still have noise on the receiver. So the receiver itself will have thermal noise. But as you're optical, you don't actually. Then you have shot noise. So this is to the quantistic measure of an optical signal. Yeah. So you don't have, we have the shot noise in wireless as well. Is anyone else listening? Maybe they call it shot noise, but it's different. I mean, it might have a different connotation. But I mean, here basically means that I'm transmitting photons. Okay? Now imagine so this is the fact that the photon has a quantistic effect in itself. Okay? So the smaller number of photons I send, the more this quantistic effect is revealed. Okay? So the point is that if I have a lot of photons, like thousands of them, then they pretty much behave like a bunch of I have a continuous signal. But as I start going to pulse which have very few photons, like as little as 11, then I have let's say a probabilistic, then the quantistic and probabilistic measure of the signal comes in, which basically means there is a probability to this photon that this either arrives or not, or even a probability of the time or arrival of this. Okay? So this is basically calculated as a distribution function. So short noise is basically because of the fact that there is an indetermination intrinsic in the fact that a photon is a photon on the time it arrives. Okay. So basically, and this is seen as a kind of as an error. Okay? Because if I back up, if my bits are all close together, there is an indeterministic nature of this. This might arrive a little bit later, and then I go to the next little bit. So this is what's called the short noise. And then there is something else is called amplified spontaneous emission, and this is due to the fact that I use optical amplifiers. And they also introduce, so they amplify the signal, they're actually very good, but they also introduce some noise. So maybe I just go and get. Just go to this. So bit rate and optical signal. So saying so the signal to noise ratio is what matters at the end when I go electrical to retrieve my signal. But in between I kind of can characterize the noise as optical signal to noise ratio. So let's see. So this probably the best thing is that. So this is a typical. This is a system used for long reach passive optical network. So this is the power I get at the receiver in dBm, and this is the bit error rate that I get. Okay. Now you can see that so for a certain power, the bit error rate that I get depends on this particular quantity, which is called optical signal to noise ratio. Okay. So basically, so this is the power I get at the receiver, but that's not enough. Okay? I need to know as well how much noise is included in that power. Okay? Because if the power at the receiver basically is that I have a signal which when is a 1 signal, I have this much of power. But then that's not enough, because if I know that there is as much noise, okay, then the difference between the power and the noise is only this much. So basically the optical signal to noise ratio told me how big is this noise, okay, compared to this. And the optical signal to noise ratio is pretty much the noise is basically due to random photons, okay, photons that sum up to the signal. Okay. So if I have my signal, imagine I have a signal which is like this. Okay. If I have random photons, so this is the signal I want. But since there are random photons that adapt to the amplifier, basically, this can become something like this. Okay. And depending on how good is the power of the signal itself to the noise, it will become how easy for me to detect those signals. So this is, for example, how the signal is affected. So if I have a good, imagine, the better the signal, the optical signal to noise ratio, which means that the lower the amount of noise I have for a certain power at the receiver, then I will have different bit error rates. Okay, suppose I have one bit error rate 10 to the minus 6. Okay. If I know that I have, for example, 16 dB of optical signal to noise ratio, then I need to make sure to transmit enough power or to build the system in a certain way that at least I receive this power. But if I'm good enough to have a system with a lower optical, so I have a system which has less noise, then for the same error that I want, I can transmit to 3 dB less of power, for example. That means that my system gives me 3 dB advantage. Now, of course, this can go up. So this is limited by a thermal noise. Okay. So my optical signal to noise ratio can be as good as I want. But so imagine I have a signal which has no noise at all. Okay, it's an extremely good signal. So the amplifiers don't have any noise. But then I still go to the receiver, and once I am to the receiver, there will be some thermal noise due to the receiver itself. So I cannot go back behind this. Okay? So thermal noise basically, this indicates that thermal noise can be small, because generally the optical signal to noise ratio is more influent. But if I try to diminish this, I will basically hit the wall on this side. And on this side, basically, what's called noise limited. So basically, my system is limited by the optical signal to noise ratio, basically by the noise created by the amplifier. And it's probably a good time to stop. So bit error rate, so an optical system, bit error rate is related to something which is called the Q factor. Imagine Q could stand for quality, doesn't matter that, for quality factor. So this basically depends on this formula, where I0 is the current that you receive, which is associated with the average current, associated to one bit, so a bit number 1. So when you have a pulse, for example. The 0,1 is what current you receive where you have no signal, so you are supposed to have a 0. And then sigma 1 and sigma 0 are the variances of this spectrum. And okay, this is assuming that we have kind of a Gaussian distribution of the pulse. So what is an optical system? You check what's your eye diagram. So this eye diagram, basically, if you check, this part like this is the pulse, which is a 1, and this part which was like this should be at 0. So basically you observe this about a certain time, so you record everything that passes through. And at the end, it's going to look something like this. Okay? So this is all the photons, or the currents basically, that have arrived to the receiver over a certain span of time. Now, if you imagine that once you get this signal at the receiver, you will have to make a decision. So what the receiver does is that, first of all, it chooses where to sample the signal. Right? So it basically wants to know if it is receiving this value or this value. The best point is here in the middle. Okay? Because there's a big difference between this 0 for bit 0 value and this bit 1 value. If I decide to sample here, for example, that will be an order position. Because basically, you see, I don't know. If I'm here, basically, no, I receive this which is in the middle, so I'm not sure, is it a 1 or 0? So basically, I have 50% chance of getting it right. If I have a 50% chance, it's as much as I switch off the receiver and just guess it. Because that's, they have the same probability. So, basically, it's going to take the decision there in the middle. The problem is that if this Q factor is bad, what happens here is that this part is quite close, become very close to this one. So the whole I diagram become very messy and positive. And basically, you can have this part all over the place here, and this all over the place here. So basically, when you make a decision here, there's high chance that you are mistaking something which is on this side for a while, or the opposite way. So the relation between the bit error rate and the factor is fixed, as given by this. This is the complementary error function, and some mathematical thing can be approximated by the error function. So I was saying before for error correction. So you can use it basically. You code your signal in advance, so your bits in advance, and then if there are mistakes, this error code can actually repair those mistakes. So they have a overhead, so you lose a little bit of the bit error rate, you're losing complexity, so you're losing complexity, so this is more complex, you have to spend more money. But actually, I mean, since they assume that you know what kind of noise you're doing, so basically say, you can do really something about it, and they work quite well. So optical design, so designing an optical link, usually I have a bit error rate requirement that I have to meet at the end. And of course I have also budget in terms of money requirement. So we look at that later. So if I want to satisfy the bit error rate, I have to consider the following factors. First is the power budget. How much power do I have? Okay, so I have to arrive at the receiver with a certain power. So this means that the power, the launching power, so how much power I put in my laser at the beginning, then I have to subtract all the losses, as fiber, connectors, I have to maintain a certain margin, okay? So I don't want to be just 0 to be left of margin. And all this has to be higher than whatever is the receiver sensitivity, which I defined from the previous lecture. Now this margin basically can change, depends on how many things you are actually considering here. So if you neglect some things in here, then you have to put in the margin. But otherwise, I mean, the real reason of margin, any loss that you can foresee in advance, then they should go here. So the margin is for things like degradation of the components, the optical components degrade and then they work less. And then other unforeseen events, I don't know, like I have a fabric cut, I have to reduce a little bit, I lose a little bit of margin. Second thing, so this is a requirement. If I don't have the power budget higher than the sensitivity, then I can forget about it. Second thing is the signal to noise ratio, which basically is optical signal to noise ratio. Basically, it depends basically when the facts that Q factor basically tells how much noise is on your optical pulses. And so if this is satisfied, then I still have to go look at that, okay? Because I could have a very high power at the receiver, so very good power, but if the noise is too high, there's nothing you can do. And this is like an information theory. So anytime you put noise in a system, you basically destroy the information, part of the information carried by the system. There's absolutely nothing you can do to recover it. Then there are other impairments. So we consider power budget, signal calibration, and there are impairments. And in our case, we'll only look at dispersion. So how do you compensate for dispersion? And there are also nonlinearities. So in general, we put something which is called a power penalty if I'm associated with these impairments. Basically it means, so I have no impairments, I have to send a certain power to get my total budget. In some cases, I could say, okay, I have some impairments, so I could consider that impairments as the additional power I have to put in here so that the system works exactly as before. Okay? So I have an impairment, so the system will work, works in a bad way. But if I increase the power, then I can get the same. So in that case, you can actually quantify everything. It doesn't always work. Okay? You would say, yeah, for dispersion, you can do it for dispersion, but you can do it from a power point of view, but from a timing point of view, which is this broadening, there's not much you can do. There's nothing you can do with power. Okay, noise amplified system. So the noise are mostly three types: amplified, spontaneous emission. Wherever you put optical amplifiers is going to generate random photons, which is an additional noise. That's introduced noise to the system. If you don't have this, then you will probably be limited by the thermal noise, likely. Thermal noise is basically at the receiver. This thermal noise is an electrical film, so you only get it when you convert the optical signal into an electrical signal. And then you have shot noise. Shot noise is basically due to the conductive nature of the signal, because photons, if there's lots of them, then you can consider them as a wave. As you use less and less of them, which makes sense because you want to use them possibly, they start behaving quite randomly. So they might arrive with a very statistical distribution. And this basically affects your system as a noise. Because basically, if you take your sampling at a certain point, but if not all the photons are arrived at that point, you kind of lose sensitivity. So beta rate and OSNR. So I was saying before, so this curve shows pretty well what's happening. Right? So this is various level of optical signal to noise ratio. You see that the lower it is, the worse is the signal. So you see, it doesn't matter if the OSNR is bad. It doesn't matter how much power you try to put into the receiver. You will be limited by this beta rate. Okay? So any power basically you increase here, just power gets practically lost. As the signal ratio gets better and better, then you improve, but then see, there is a point where even if this is extremely good, you have the thermal noise of the receiver, so you won't be able to go any better than this. That's because you go back to electrical. Then there's also shot noise, but that's on higher powers, so we shouldn't see that. So what this tells is that, so I want the rate of 10 to minus 9. Okay? If my signal OSNR is really good, or 30 dB, then I'm limited by this thermal noise, and I need this 19 dBm. If I have some signal noise ratio, then I start working on a different curve. And you see, it can go bad very quickly. Okay? So like 16 dB, you can get 10 minus 9 anymore. So you need this. And this tells you basically how much power you have needed to receive. So Q filter from SNR, so the Q filter is that it's quite important to realize, to make the calculation of the bit error rate in the lead. How do you get this from the SNR? Basically this is done by this formula. So this is in decibel. Q in decibel is the OSNR plus log of these two quantities. Now practical purposes, this is minus 2 dB. Easy. So this is the bit error rate. So you need to know what your Q is to know the bit error rate. And in dB, this can be expressed by that. So basically, you know your OSNR, then you can know the bit error rate. Signal generation. So set power budget. So this is the first thing you want to make sure it is satisfied. Okay, and then you can check the signal to noise ratio. But this has to be satisfied. So okay, you check that. So you can launch, your input power depends on how much power has your laser. And even if you think of amplifying that at the beginning, you can't really, because the more you amplify, the more you have no linear effect. And I mean, we are now neglecting them, but you can only neglect them if you don't put too much power. Otherwise, they become natural, and then you cannot neglect them anymore. So, and when is your signal generation? So you go there, you buy your laser. The fiber loss, the fiber has certain loss. Nothing you can do. If you have to go certain distance, you have to go certain distance. Then your margin, you have your margin, which is 3 to 5 dB. And then your receiver sensitivity, which is also limited. So if this is not satisfied, what do? You can't shorten the fiber particles, you have to get there. So that pattern is basically what you have to do, you have to and you have to amplify. Okay, this is just one example about the sensitivity that I was saying before. Okay? So imagine I have a 0 dBm input power, 25 dB of fiber loss over 100 kilometers, and a margin of 5 dB. That means that the received power has to be at least minus 30 dBm. Sorry, the received power that I get at the receiver is minus 30. Now, if the receiver sensitivity is such that to get this bit error rate, I need minus 27 dBm, then there's pretty much nothing I can do. This is 30. No, I'm missing 3 dB. Okay, so I need to change something here. So what I can do is amplify the signal. So in some cases I can actually amplify just before the end. In some cases you have to amplify that before. And we'll now look at that. Now there are different ways of regenerating a signal. So this is one, they're called by R, term of regeneration. And if you use the SONET or STH standards, they have 1R, 2R, and 3R. I'll show them later. Now this is the basic, and this is still based on electrical amplification, which you don't do anymore now. But just to show you basically what this is. So you have your signal, optical signal, after going through fiber, just decreases. So what it does is basically converts to the photodiode, optical to electrical. It's all analog signal. I have an analog amplifier, boost them up, and basically I remove this signal, I remove my laser, trying to build something like that. Okay, so that's what people used to do at the beginning. And now, this is not used at all electrically, for the simple reason that if I do that electrically, I need one amplifier for each channel. So if I have a fiber with 50 channels, I have to, when I stop, I have to amplify all 50 of them. But you know, that's the general idea of what's amplification is. Now, I mean, every amplification now is basically an optical amplifier, if you are an amplifier especially. So an optical amplifier is basically a laser. So it's a laser where people have removed these mirrors here. So the signal cannot bounce back and forth anymore. So just go and leave. So the operation is pretty much like a laser. So you have a current pump, which creates an inversion of population, which basically means all electrons are excited here and ready to release light. And then there you go, the yellow photon goes by, it stimulates another yellow photon, there you go. Different frequency, goes and stimulates a different frequency, and then there you go. So the first advantage you see, well, it's optical. Second advantage you see, I can actually have photons of different wavelengths. So visually means I can actually put different channels all together, and it doesn't care. It just multiplies photons. So they just keep them as they are. And so that's basically that's the main advantage. So these type of amplifiers are called they are SOA, semiconductor optical amplifier. So they are basically a semiconductor, exactly like a laser. They use current to pump up, and basically work exactly like that. Now, a new amplifier that was developed a few years ago now, about 20 years ago, is the Erbium doped fiber amplifier called EDFA. So this is let's call it all optical amplifier in the meaning that I'm not using current to pump up the electrons. I use another laser. So I have a light which pumps up the electrons, and then the other light gets amplified. I mean, I still need electricity because the first pump needs electricity. But it works basically has some good characteristics, and it has you can build it with a fat gain with some tricks. It has quite low noise figure, which is quite important if you put them in a long, if you use a lot of them for a long distance. And as well, it's quite important it has a low crosstalk. So basically, if you're doing WDM, each signal does not affect any other signal too much. While in SOA, you can almost not do any WDM because there is so much interaction.
What's the C-band again?
Oh, sorry, C-band is the band, slide shows that now, but so the fiber has kind of windows where the loss is low. Okay. So people tend to use those windows. C-band is it's a band between 1520 and 1555 nanometers. It's basically it's like a channel frequency band.
Okay.
But imagine that in that band you can fit about 80 channels if you want.
Okay.
So it's quite large. But so the idea is that the amplifier works well only in the C band. Then there is the next band, which is L band, which is roughly a little bit bigger, but roughly the same.
Okay.
You can build a DFA which work on the L band, although they're not as good. So usually a DFA, in any case, is always connected to the C band, which is the band used for telecommunication. So combined with the WDM, this ADFA is actually what was the main technological advance, which has led all telecommunication field advance. Because basically, it means you can put a lot of channels together in the same fiber without using another fiber. And with the same amplifier, well, it's slightly more expensive, you can actually amplify all the signals that go through. So that was a big advantage. So again, the big advantage is that it's optical and it amplifies all the wavelengths that it goes through. So no need for each amplifier for each channel. This is a little bit how it works. So it's a length of fiber dotted here erbium, which is already there. So okay, so this is the C band, 1565 nanometers. That's the L band. So the way it works is basically you have a piece of fiber dotted with erbium. So you pump this 980 nanometer light from a 100 laser. This pump basically, all the electron goes from the basic band, the right side up here. What happens then is that then from here to here, so these are energy bands inside the material, and these are the gaps in them. So there are different bands and different gaps. So the pump source basically goes here and separates all the fiber, and then it gets thrown out here. So it pumps all the electrons here. Then there is an initial relaxation time. So basically, I'm not sure if the emit lighter is just a phonon thing, so it's just create vibration and heat. But anyway, basically the electron go back here, either is light or not, I can't remember at the moment. But then this level is called a metastable level. So all the electrons that go here, they stay there for about 10 milliseconds, which is a very long time, in optics. So this is quite good because if they can wait 10 milliseconds, then it means, I have more chances that every electron will be, how do you say, so every electron will generate light, coherent light, right? So we'll wait for a photon to pass and then duplicate itself. Okay? If this is very small, you can imagine that as the thing goes up, there's a very chance it goes down before a photon passes. And if it goes down before the photon goes, that's basically noise, okay? Because it's not replicating anything, it's just generating a random photon. Right now, the fact that they are here about 10 milliseconds, the first advantage is that the spontaneous emission is not as high as in other amplifiers. And the second thing is that it has the reason why it has low crosstalk is related to the fact that this 10 milliseconds is quite a high time. So basically means that the amplifier doesn't react very fast to all the modulation of all the other channels. So since these things are 10 milliseconds, it can be always smoothed out. So basically, it means that if I have to sign two channels, this channel is not going to be printed part of it on the next channel. Okay, this is the advantage. So as we said though, it generates, some photons some electrons will combine randomly, will generate random photons. And random photons are basically noise. So this is basically much what happens. I mean, as I made signal from the laser, the signal is quite pure actually. So you can imagine there's no very little noise there. Then once it goes to amplifier, so the signal is amplified. But then you see this is all spontaneous emission noise. So this is the power of the signal up to here, and then this is the power of the AAC noise. And the signal to noise ratio, especially the relation between the power of the signal and the power of the noise. Then what happens, okay? So now I have to go a certain number of kilometers. So I'll have a certain loss, and I mean each amplifier has a maximum gain. It be 25 degrees of this. It's quite high, between 20 and 25. So what will happen if you have to go quite far away is that you'll have some fiber loss, and then you lose 25 degrees, for example. Then you put your amplifier, and you gain them away. You lose them, you gain, you lose, you gain, and so you go on. Now the gain of the amplifier is actually related to the noise as well. So the more gain you have, the more noise produced. So if we'll show you now basically going through this deteriorates the signal to noise ratio. And one thing you can do to improve that is to space the amplifier. Instead of, for example, putting every 80 kilometers, you can put them every 40. And these are a huge advantage in terms of signal to noise ratio, for sure. And in any case, if the signal to noise ratio gets too bad, then there's nothing else you can do. You have to regenerate the signal. So stop the link, read the bits, and then create an array. So that's basically what happens in a channel amplifier. So the noise figures of an amplifier is a quite important measure for a power budget and signal to noise ratio budget. And it basically tells you how much noise does the amplifier introduce in the system. And this is the same for electrical stuff, for the whole system. The measuring the P depends on the amplifier type, gain, and so on. For the FA, roughly, it will be about 5 to 6 dB. So that's my channel amplifier. So before we've seen the first amplification, but then what happens when the signal goes through? The signal goes through, so both the noise and the actual signal get, they actually get, well, some of them get absorbed, but they get, the light associated with them basically get lost, so both powers are reduced. It's a bit different from electrical. Because I think in electrical, so you have the electrons which still moves depending on the temperature. Okay, but in the fiber, that doesn't happen. So the fiber doesn't actually generate photons which are noise. The photons are generated here by the amplifier. So as you lose power here, you lose power there as well, which is a good thing. Then you amplify. So if this didn't introduce any power, if this didn't introduce any noise, then you would go back exactly to this. And then your signal to noise ratio will remain the same all over the place. It would be great. That doesn't happen. So you have the same situation of this, plus this amplifier adds its own noise. Okay? And as you go on, it's the same. So you can see the signal gets hidden more and more into the amplifier. So that's why you can't use just as many as you like. How do you calculate the signal to noise ratio? So this is the nice figure generated by a chain of amplifiers when you put a lot of them all together. This is the number of amplifiers you have in the chain. Noise figure of each amplifier, and this is the length of each span between the amplifiers, and that this is just the loss of the fiber. So from this actual equation, you can see very well that if you have the same, like if you have a 500 kilometers link, the signal to noise ratio you get if you use 80 kilometers is much less than the signal to noise ratio you get if you use 40 kilometers basically. That's because you can understand very much that if my signal has traveled a lot once it arrives here, it's actually quite small. So if the amplifier is always going to produce this type of noise, if the signal is quite low, it's already quite even. While if the signal is a bit higher, then the noise created is relative to the signal is actually much less. So that's there. Okay, then there are some more calculations. So this is now the noise figure of the chain, but what you are interested in is the optical signal to noise ratio when you are at the receiver, because that will tell you how many mistakes you make. This is if you have one amplifier, so launch power, loss, noise figure, and then you have this 58 dBm, which depends on quantistic parameters that basically come from the optical amplifier. So, and if you have a chain, you want to calculate the OSNR, basically it's pretty much embedding this one into this one. So you have power launch and loss, NF of each amplifier, then again as here and so on. So basically you can calculate the signal to noise ratio on that basis. Power budget, so remember power budget always has to be calculated, because you have a certain receiver sensitivity. If you don't get that, you don't get anything. And this is quite easy. So I was saying before, so two things you calculate are the OSNR and the power budget. OSNR you calculate through this formula. Power budget you calculate through this formula. Power budget is extremely easy. It's basically how much power you put at the beginning. So, and then the loss of one span of fiber plus the amplification minus the loss plus the amplification. So basically you sum up each part. And then you remember your margin at the end. And this has to be higher than the receiver sensitivity, otherwise it's not works. So there are other things to do beside amplification. So something called 2-eye signal shading. I don't know how often this is used actually. So the shape is done electronically mostly, some people tend to do optically. That's good. So it's pretty much the first stage is the same, you amplify, then you basically pass this to a digital gate, which basically reshape the signal. And I think it actually gives a 1 or 0, so you actually make a decision here. The only thing that this doesn't do, it doesn't retime the signal. Okay? So it doesn't sample the signal and decides if this is a 1 or is this a 0, and will recreate a complete path. So it doesn't do the retiming. So we basically mean that the jitter, which basically means how much the signal moves in this way, is not eliminated. So this process is transparent to the bit rate, okay, because I'm not sampling them, so I don't need to recover the clock. But it's not transparent to the modulation, which basically means if I'm using a certain modulation in the system, and then I decide I upgrade the system and I use a different modulation, then that doesn't work. 3R is signal retiming as well. So 3R is pretty much getting the signal, analyze the signal, get the bits 1, 0 out, and then remodulate the laser again. So basically, what you do here is that you actually have the timing recovery as well. So this signal you get at the end is basically, it's like totally new signal. So you have basically the 1 and 0 bits. Now this is actually quite important because what's the problem here? I mean, when you have amplifiers, there might be a situation where you realize, okay, my signal to noise ratio is too bad. Okay, I cannot go ahead putting amplifier. So then the only thing you can do is, but before it deteriorates, you can stop the signal. Okay, maybe you get a bit rate of 10 and minus 15, which is quite low. And then you can reinitiate the signal. And then what you do, you basically just sum up at the end of the link all the bit error rates. Okay. It's like basically have a new link. And then you realize how much bit error rate you have there. Okay, the link is terminated, you write it aside, and then you start calculating for the next time.
How do you decide? I mean, so basically you're checking the bit error rate, but every amplifier doesn't check the bit error rate.
No, this is when you do the design of the system.
Yeah. Okay. So
you have a paper
only for fixed networks.
Yeah, exactly.
Yeah.
Now there is things about dynamic networks which are come with optical switches, but it's actually one of the main problem is like if you switch a signal that was going this way, and now it goes this way, and maybe it goes a different distance, then how do you know if you can do it or not? That is actually a problem with this dynamic networks. So the regeneration, as I was saying, is basically stop the signal, check what's your bit error rate, and start again. So once you stop the signal, that's the only thing that you can do to improve the signal to noise ratio. Okay? So you don't improve the signal to noise ratio of the first part, because whatever you lose in information, you've lost it. But the trick is that you can do that before the bit error rate gets too bad. Because if you can stop it at 10 at minus 15, that's a really good value. You're happy with that, and then you go ahead. The important thing is that if I have a multi-wavelength system, I put regenerators. I need one for each wavelength, for each channel. So if I'm around 80 channel system, you need 80 regenerators up at the same spot. So that makes it quite expensive. So the second thing is that you have to calculate for dispersion. People say that you should take a break every half an hour. Do you want to take a break every half an hour? Go ahead. Actually, you're supposed to write a question, but you should be supposed to write a question that you want to be answered. I should answer that here. But
it's a good idea. It actually is a good idea.
Good question. What's the meaning of
yeah, actually, you have any question?
Do we have any questions?
Yeah. Anything you want to ask? Do you have to go back? I don't know. Go back to the slides.
So what gets used in Sonnet STH?
What's that for?
Sonnet STH, which kind of region?
You can use actually the deal with both all of them, 1 hour, 2 hour, 3 hour. It's up to the designer to decide which one they want to put, and each one have a different cost. So it's all quite complicated. I think there are optimization tools that actually tells you what's your best option. The only problem with optimization, of course, you optimize for a particular situation. So if anything changes, which usually doesn't. But if you want to create now a dynamic network, all this optimization stuff doesn't work anymore.
I guess you would just like try to keep the maximum loss under a certain.
Yeah, you could do that. Yeah, but the problem is that either you could design your system for the worst case. That's going to be quite expensive probably.
Yeah.
In other cases, the idea is that in a network you can have multiple routes to go from one place to another. So in theory you could even choose what's the best route to go there for this bit error rate. And if you have a lot of, if your signal is still quite good, then you can try to go on the worst route possible so that you leave the good route for signals which haven't got a good one. So it's still an optimization thing. But even as an optimization, the problem is that you don't have all this information that you have when you design a single link. Okay, a single link you design and you know everything about it. Apart from, of course, some things which are non-deterministic. But if you have things going in and around, it really depends what you're switching. So there are some ideas where we actually measure the signal at certain stages. You can measure the power, no problem. But you need to measure signal to noise ratio at least. And maybe the dispersion, then it becomes expensive. Don't know if you can do it all optically or you have to. I think what people do, they take a percentage of the power off and then they put an electrical receiver which measures some kind of these things. But then you can only do one. Once it's electrical, you go to one device per wavelength. So it's all quite complicated. Cool. So dispersion. So we talk about how do you make a link depending on the power budget. So you need power budget, signal to noise ratio. The other thing that happens is that there's dispersion. There's actually another thing as well, which is non-linearities, which I'm not going to deal with them, which are just too complicated. But dispersion is very common. Okay? So non-linearity, if you use low power, well, if you use reasonable power, if you don't have too many wavelengths, you can kind of get away with that. But dispersion, that's not going to get away with. So dispersion, talked before, so this is your pulse, goes to the fiber, and because the fiber is non-linear, basically different frequencies tend to go at different speed. Basically what happens is that since your signal is not just one sinusoid, but is made of, so like if you do the Fourier transform, you get kind of a bandwidth. Basically each part will have a different speed. What happens in time is that this is the signal you put in and this is what you get out. So basically it's spread out and it's lower in power. The spread of the optical pulse is this delta t time, which is given by the dispersion coefficient of the fiber. This depends on the fiber you use, it's a value. Fiber length and signal bandwidth. So you multiply them and you get what's delta t. For practical purposes, what you actually look at, you look at the dispersion per unit bandwidth. So you look at this parameter. And the problem with this is that if the signal spread, okay, you lose some power because it gets flattened a little bit. But the main point is that if you have another signal, another pulse here, they just overlap. And that's called inter-signal interference. And with that one, there's not much you can do. You can't increase the power, it's just a time issue. So there's some values that, okay, this depends on a lot of complicated parameters. But what I've done, people, for example, for Sonic SDH, they basically tell you, if you have 10 gigabit, you use this type of a laser with this bandwidth, and you use this modulation, then you can have tables which tell you what's going to happen. So basically, in order to be tolerated, basically you have this distance by L as kind of to be less than a certain unit. So I have the possibility, when it comes to dispersion, on measuring a link or building a link. If the dispersion is smaller than this limit, and I can say that's great. I don't have to do anything. The only thing I have to consider is that there is an impairment due to the dispersion, which is the fact that this signal is lower than this one. But if the time overlap is fine, so the table tells me, okay, the time that overlap is fine, then you only have to consider about this power. And of course, if you don't have that power, then it's a problem. But usually it's 1 or 2 dB. Should be okay.
Would the power loss due to dispersion be accounted in the margin or in the...
No, you can't. No, you have to account it before the margin, the loss, because it's something quite deterministic. So it wouldn't be fair. People put in the margin and then increase the margin by 2 dB. So if I'm not within this limit, then I have to do dispersion compensation. So this is what I was saying about dispersion power penalty. So the amount that can be tolerated on a link depends on data rate, spectral width of the laser itself, modulation time, spectral width of the pulse, and if you do an external modulation or a direct modulation at a different data. But pretty much, like usually what you have is 1 dB or maximum 2 dB. What happens is basically when you have 2 dB, then the ISI, over 2 dB, the ISI gets too bad. So basically, it's not worth it anymore putting any power. But these are examples. So this is your bit rate, 2.5, 10, 40, 10, 100 gig. This is the protocol. So basically, this is just as. So this is a sonic, this is an Ethernet, that is an NLZ, so no return to zero. So this is the dispersion limit you have. So picosecond per nanometer. So for each nanometer of bandwidth, that's how much you can tolerate. And this actually helps you even more because it tells you if you're using this type of fiber, a specific fiber, then this is how far you can go. Okay. Only considering 1 dB. If you look at the 2 dB one, okay, it's the same as this. Basically, it tells you how much you can go, but then you have 2 dB penalties. But this pretty much is as well the limit. Okay? You cannot go over this. You look at the difference, like 2.5 gig, you can go almost 2,000 kilometers. You multiply this by 4, and you can go just about 100. You multiply it again by 4, you can only go 7 kilometers. The 100 gig, you basically can do 1 kilometer, which is pretty powerful fiber. Pretty useless actually. But then you see that there's not a lot of other things that people have discovered now. So apart from 100 gig, you get all other sorts of problems. But now people, on this kind of system, the people start doing something which is called coherent detection. Okay, when you do coherent detection, basically you can do a lot more stuff. I'll say about that just at the end. So in any case, if I'm above this limit, then I have to compensate dispersion. How do I compensate dispersion? It's actually quite easy. So the normal fiber has this dispersion coefficient, plus 17 picosecond per nanometer kilometer. I can build fibers which have a dispersion which is the opposite of this one. So this is 17, and actually I can build them with a quite high opposite dispersion, so that if I have 80 kilometers of this, then maybe I can only use 5 kilometers of this. And you see, okay, that's what happens when the pulse spreads up, it's reduced, it spreads and it's reduced. And this is the accumulated dispersion. So these are some positive slope and a relatively low slope. So it goes up this way, and then as I go on this one, the dispersion goes back up to 0. Of course, I have to know exactly how much fiber I need. In practice, I think that I don't know. I think rarely people actually cut the fiber as much as they need. I think they kind of come in boxes and tells, okay, you can disperse with this a certain amount. And then you optimize, and there's an optimization tool, you decide where to put them, and so on. Plus, I mean, if this is not exactly 0, it's fine, because you remember, you still have like this kind of limits, you still can tolerate quite a lot of dispersion. But this is pretty much what we use. The other very good thing, So the other good thing is that you can actually compensate multiple wavelengths at the same time. So as you can amplify them at the same time, the dispersion works on them the same way. It's basically like I have a transfer function, and then I have an opposite transfer function. The only thing is that they're not exactly the same. So it works very well, for example, if you decide to calculate your dispersion for the central frequency. So if you have 40 channels, you calculate the dispersion for the middle channels, then what happens is that the more you go to the edge, the more discrepancy is there between this slope, this slope here and this slope here. So they're not exactly the same in terms of, it's not just the slope, it's also another thing when you do the derivative of that. So how this changes in frequency. So you can't do much exactly, but usually you can do quite well. Other important thing is that dispersion fiber. So you introduce fiber, okay? So you introduce additional loss. Plus, not just that, the dispersion compensated fiber it actually introduces even more loss in the normal fiber. And the other problem is that you're going to have nonlinearities. So actually, I think DCF will even introduce worse nonlinearities if you calculate them. So in theory, I can actually put all the dispersion compensating fiber at the end of the circuit. Okay, I have 12,000 kilometers, I could only put it at the end. In practice, because of these nonlinearities, it's much better if I space them. And usually what you do is that, I mean, you need amplifiers anyway. So what people do usually, you put this together with the amplifier or whatever you put amplifier. I mean, this is even better. This is totally passive. This is pixel fiber, so you can put it wherever you want. The thing was saying for now with coherent system. So the problem, I mean, there are some electronic dispersion compensation. So basically means that the signal is like this, and then you do some clever stuff like sampling, and you know you have this digital digital processing, which basically try to reduce the dispersion. They work quite well. But if you use them with coherent detection, which basically means you just check how much power you have on each pulse. Once the overlap is too much, there's nothing you can do because you're losing. So by doing normal what's called direct detection, you lose all the information of the phase, what happens to the phase. Okay. So in theory, dispersion basically just means if I have a transfer function h, what do is that at the end I just put something which has a transfer function of 1 over h, and that's totally compensated. But the 1 over h, it basically is not just made on the power of the signal, but also influences the phase. Okay? If I do direct detection, basically I just check the power there. What happens is that I lose total information about the phase of the signal, so I cannot do anything about the phase compensation. So there are some compensation, electronic compensation, which work on direct detection, but they basically, I mean, there's only so much they can do. While if I use coherent detection, basically I now know also what the phase is, so I can actually totally build inverse function. Now it's not easy, especially because these are quite expensive. These are used for a high-speed system where it's not convenient to do the rest. But it's difficult to go have something. Plus, sometimes you need oversampling. So I mean, it's very hard to do oversampling when your signal is 100 gigabit. But still they are advancing on this, like long haul links, which are quite expensive. They now tend to use this, so they kind of are getting their way. Compensation calculation. How do I calculate the dispersion? That's very, very easy. So then the dispersion I have for each nanometer on a piece of fiber is basically the coefficient multiplied by the length. This is. If I want, now I'm talking about this fiber dispersion first. So to compensate, basically, I have to get another fiber with a certain VCF, and then I need to calculate what length do I need so that I have exactly opposite of this. So basically, I have first dispersion plus compensation has to be equal to 0. Example, links are 100K, dispersion of normal fiber 17. I get 11,900 units of dispersion. So this fiber that I have is pretty much fixed. So how much length do I need? Just divide this by this dispersion and get about 80 kilometers. Now remember that the dispersion, for example, the loss of this fiber now is 0.8 dB per kilometer, not 0.2, 0.5. So basically I actually add 63 dB of additional loss. That must be on the power loss.
I mean, here, like, you were just considering the length of the link that you originally needed, and then adding more length. Could you just like shrink the original fiber and use part of the fiber?
Yeah, I thought actually about as well at the beginning. The only problem is that that's not the way people do it. First of all, usually dispersion compensation comes in boxes. You put it close to one fire. The second thing is that that kind of dispersion fiber has certain properties, and they might, with time, they might actually get better fiber which have better properties and so on. If you put that in your link, then that's in the link. There's something
you're going to make.
Or if you want a different link and you don't want to use the dispersion DFC, you want to do electronic compensation. That's actually part of your link. There's nothing you can do.
Yeah.
But the idea is that your link is the same. It's still in pieces, but it's one type of fiber.
Okay.
And then we do the compensation there.
So I was going to ask that. So they don't actually lay this stuff because that would make your fiber specific to a certain frequency or a certain.
Yeah. Well. Yeah. So that is where the length, the length you want to use, you might want to change that at some stage.
Yeah.
Put a different dispersion or change the mapping, introduce more
I change the wavelength of the laser.
Well, you see, you can compensate for a band, but that's as well.
Yeah.
I mean, if you want to optimize for a different band, for example,
Okay.
then you can't do that anymore. But that's a question I have to do as well. So that thing is that when you use multiplexing most WDM, WDM means you have a laser at different frequencies, you modulate them, multiplexer, you put them together, and they all go on the same fiber. The multiplexer, this is our own passive components, and then you get the gain more signals. So basically just putting more signals together on fiber. That's an example how one of them look like. That's more actually. So the activity, which is one of the standardization agencies that looks especially at telecommunication, has defined the spacing of these wavelengths, so how far apart these should be. Right? So there are basically two types of radios, coarse WDM, which is use cheaper components. So the spacing is 20 nanometers. So basically means that in the whole bandwidth that people normally use, so this is a huge bandwidth, I can only take in wavelengths. I mean, comparison, C band, I can only fit 2 of those wavelengths. And L band, I can fit 3. So these are used usually when I don't have to put on optical amplifiers, when I want cheap components, okay? And then I can use this. These are quite imprecise as well. That is advanced WDM grids, which use different type of components, and they are defined in gigahertz rather than nanometers, but this is roughly what it's about. So here as well, you can have 100 gigahertz, which is these are all slots, okay? And which are days of 50, which is half of it, and which one you use depends on which technology. Like at the beginning, they were using 100 gigahertz because the components were not good. Then they start using 50, and now they don't know what to do because now they realize, if they want to go faster than like 100 gigabit and so on, they can't keep squeezing it. Right? They have higher auto-modulation, but it's not easy. So you basically need to go enlarge your bandwidth again. But if you have equipment which cuts your signal 50, cut basically is 50 in 2. You can't put a larger signal. So this is this kind of approach that we were looking at now. Anyway, dense WDM C band. If you have this 100 gigahertz spacing, you can get 40 channel. If you have this other spacing, which is actually quite used now, you can actually fit 80 channel in the C band and 80 in the air. And there are even smaller ones that are used not really for communications, but they use on research environment. So what are the issues at WDM? Very, very quickly. There are a few issues. So one, for example, is the fiber misalignment with when I use the multiplexers. Okay, so the filters, it's very hard that I can build an optical physical device which has exactly the same bandwidth. I mean, here we're talking about a fraction of nanometers. So some of them will be slightly off band. What happens is that the more of them I go through, the more they kind of skim the signal. So I lose part of the signal. And then basically, if it gets too much, I have to stop regenerating. I'm losing information. Second thing is what's called crosstalk within the optical component. So I have a signal. In theory, this should divide exactly all the wavelengths on each different fiber. What happens is that there's a leakage. So part of this actually goes on this wavelength as well. And then this goes to a different phase shift. And then when they combine, basically this kind of creates some kind of noise. Then there are nonlinear effects. I have 3 wavelengths. They kind of interact with each other, so they generate wavelengths at multiple, well, some of them. And basically you have noise, basically you produce noise. That's what you have. In terms of benefit, well, the same fiber can handle all the channels. I can use CWDM transmitter, which are cheap. They are not thermally controlled, so they can move quite a lot. So that's why you need 20 nanometers. But usually you use them if you have to cover distance up to 120 kilometers, because you just put a transmitter on one side, the receiver on the other side, usually it works very well. With WDM on the other side, require better laser, very stable. They are thermally controlled, so they can't switch around because otherwise they don't do the next channel. And they use basically when you actually have to put a huge amount of channel in the system and also for the whole system. Now, commercial system. This can be achieved quite easily, economically at least. So you can put 1.6 terabyte on data rate in one fiber. Just use C and L band, for example. Now, if laboratory experiments actually reach about 70 terabit per second or 250 kilometers. But that's not very useful.
250 kilometers before regeneration, 250 kilometers stop.
Yeah. I mean, regeneration basically means once you regenerate, you're back in business. Now this is, I just created this, okay, I'm not going to show this brochure last time, but so how do you calculate the optical link? So you have to calculate your optical link. How do you start? Where will you start? So the first thing is that you start actually from the dispersion. Right? Because if the dispersion is tolerable, yes, fine, I don't do compensation, but I have to consider the dispersion, the power penalty due to the dispersion. So I put it aside, one of the view of TCD, and the other will be if it's not, then I have to compensate the dispersion using the fiber, which we saw before. Okay, compensation is done. What's next? Power budget. Is power budget sufficient? If it's yes, great, fine. If it's not, then I have to start compensating the loss using ABF phase. What's the problem now? If I use ABF phase, then I'm going to deteriorate my SNR. So, third thing to check is that is SNR sufficient? If it's yes, great, go ahead. If it's not sufficient, then what do I do? Well, there's a couple of things I can do. First, I can try to reduce the spacing between amplifiers. This means I need more amplifiers, spend more money. But I can improve a little bit that SNR. And I mean, ideally, I tried a few times to see if I can get something that wrong. If I can't, then I have to put regenerators. Okay, when I say regenerators. Okay, then I have SNR sufficient, yes. Last question is that, okay, do I have enough money to fund? Okay, that's always. If I have enough money, say, cool, it's finished. You don't have to save money, you know. That's your budget. If it's not, then you're in trouble. Like when I could have done. Imagine I have a 40 kilometer link, and I use all the best components so that I get all yes here, yes, cool. But then I say, okay, now that's only a 40 kilometer, only good, so much money. So it could be that you just used two good components for the part. So basically what happens is that no, then you have to try and use cheaper equipment, and then you have to go back all the way here. So maybe I could use a laser which has worse dispersion, but it's cheaper, and it's probably for the distance is good enough. So at the end, what happens? If I manage with the budget, yeah, it's fine, it's good. Otherwise it would be, you have to go back to the management and say, yeah, it can be done, need more money.